Another example of physical applications of integration is going to be these types with respect to work. And let's just say, for instance, that we had to push like an object upon some sort of static. So we had to push it on like a flat surface. So let's say you have a box and we're pushing it. All right. Then we could just use our formula, force times distance, all right, to be able to push something on a static if it was just flat. However, let's say it's a variable. Okay, so for instance, we're going up like a variable force. We need a variable force. So like, and you guys could understand that to go from here to here would be a different force to be able to push from here to here, and then also from here to here. And these are like our delta x's. So this might be like delta x3 and delta x2 and delta x1. Okay. And so if we knew the force function, like the force there and the force here and the force here, then what we could do is we could just segment and partition those. All right. Now, this sounds like a familiar story because what we'd like to do is to be able to partition them into an infinite number of smaller force times distances. And so if we know the force function, if we can model that force over the distance, then we could just take a Riemann sum. Okay, so this would be like our infinite number of partitions. This would be our force function, and this would be the distance as delta x sub I approach 0. Okay, so as the number approaches infinity, then the partitions approach 0, or the distances. And so we just get this work formula right here. One other application that we're going to use with respect to work is Hooke's law. And Hooke's law basically says that if we have a force, it's basically for a spring, it's going to be proportional. So K is that constant of proportionality to the distance displaced from equilibrium. Okay, so X is going to be the distance that's going to be from equilibrium. So we'll take a look at that in a few moments. But for right now, let's just take a look at a few basic examples of being able to work with work. So how much work is necessary to move an object from x equals 1 to x equals 3? So let's say x equals 0 is the origin, and this is measured in meters in the presence of a force given by this variable force, 7 over x squared, acting along the x-axis. And so we just use this formula to set it up. So we're going to have our integral, so our work is going to be equal to 1 to 3, 7 over x squared dx, which is the same as the integral from 1 to 3 of 7x to the minus 2 dx. And now we can just evaluate. So we're just going to add 1, divide by the new exponent. Right, so this is going to be 7x to the minus 1 over minus 1 from 1 to 3. We can back substitute. We can move this back down to the denominator. And so we would get negative 7 over 3 minus a negative 7 over 1. Or if we got common denominator, that would be negative 7/3 plus 21/3, or 14/3. Now, notice that the distance is measured in meters, all right, and the force is newtons, all right. So, so basically, like these would be like our newtons, and this would be our meters, and so we end up with Newton meters. Okay, so Newton meters, otherwise known as joules for our force, okay, or for our work, excuse me. Okay, so the force is in newtons. A lot of times when we get the answers to this, the answers are going to be in joules. All right, another example for us. Let's say that suppose we have a force of 40 newtons, and it's required to stretch and hold a spring that measures 0.2 meters from its equilibrium position. And we're going to go through and just work through all these parts. So first, we want to try to find the spring constant, K. How much work is required to compress the spring 0.4 meters from equilibrium? How much work is required to stretch the spring 1 meter from equilibrium? And then finally, how much additional work to stretch the spring 0.2 meters if it has already been stretched 0.2 meters from equilibrium? Okay, so A is the easiest one. It's just algebraic. Remember, we have that the force is equal to kx, where x is the distance beyond equilibrium. Right? And then f of x is going to be our force. And so in this case, the force is 40 newtons. We don't know what k is, but we know that x is 0.2, right? And so in this case, we would just divide by 0.2, and we end up with 200 is going to be equal to K. All right, so that's going to be our spring constant for this one. Really easy to set that up, right? 200 equals K, not 200K, right? Now, if we wanted to compress the spring, our force function, so this is the spring constant, okay? So ultimately, our function f of x is going to be equal to a to b for the spring. 200 is the spring constant, and x is going to be the distance beyond equilibrium. Okay, so that's going to tell us how much work is necessary to stretch the spring, all right, and beyond some distances. All right, so in this case, for the first one, we want to go and compress the spring 0.4 meters. So that would be 0 to negative 0.4 200x dx. And in this case, this is really easy to integrate. So that's going to be 100x squared from 0 to negative 0.4. The 0 just cancels out. So we get 100 times negative 0.4 squared. And I believe that negative 0.4 squared is going to be 0.16. And then we just move the decimal point 2 places to the right. Okay, and that should be 16. And remember, since we have newtons and we have meters, then this is going to be in joules. All right, if we wanted to answer. Okay. All right. Another example, and this one's probably easier. How much work is required to stretch the spring 1 meter from its equilibrium position? All right, so we have 0, and we want to go 1 meter beyond equilibrium, so that's 0.1. And we still have 200 as the spring constant dx. And so this is going to be equal to 100x squared once again, from 0 to 0.1. And then we can just substitute 0.1 in and square it. I believe that this is going to be 0.01. So if we move the decimal point 2 places to the left, this should end up being 1 joule. All right. And then finally, the last one we have is how much additional work is required to stretch the spring 0.2 meters. All right, so we know that it takes a force of 40 newtons. And if we really wanted to find the work, we could. But let's just assume it's already been stretched 2 meters from its equilibrium. All right, and so the integral for this, we're starting 2 meters or 0.2 meters from equilibrium, and we want to go an additional 2 meters. All right, so we're just, or 0.2 meters. So we're just going to add 0.2 to that. And that should be 200. I was getting ahead of myself because I was thinking of the antiderivative already. Right, and this is really easy. So we know that this is 100x squared, 0.2, 0.4, right? And so this is going to be 100 times 0.4 squared minus 100, 0.2 squared. This is 0.04, so this just works out to be 4. This is 0.16, so this works out to be 16. And by multivariable calculus methods, 16 minus 4 is going to be 12. We're still in Newton meters, so we have 12 joules. All right, so hopefully those are 2 elementary examples as to how to go through and do some of the work problems. All right, so a really basic one where we just have a force times a distance, and then where we're starting to use Hooke's law to be able to solve these types of problems with spring problems. All right, so in the next video, we'll take a look at a few more spring problems, and then we'll move on to some other applications as well.